this is Miss List, and we are looking at 1.8, which is the last section for Unit 1 of AP Chem. The title of the section is Valence Electrons and Ionic Compounds. So in an ionic compound, an ion is one of the types of bonds that we learn about in AP Chem, it always involves a transfer of electrons, and that transfer of electrons always goes from the least electronegative to the most electronegative. And that should make sense if you remember that electronegativity is the desire of atoms or a group of atoms to pull electrons towards it. So it makes sense that it's always going from the least electronegative to the most electronegative. Oftentimes, this results in an ionic bond being between a metal and a nonmetal, where those electrons are being transferred from the metal over to the nonmetal. And that's because nonmetals tend to be on the right-hand side of the periodic table, and they're going to have greater electronegatividity compared to the metals, which tend to have lower electronegativities. Whether or not an atom will gain or lose electrons has to do with its electron configuration. So the idea here is that a loss or gain will happen so that an atom will get a complete valence electron shell. For most atoms, this means that it's going to be S2p6. So S2p6 means that I would have 8 total valence electrons, which is why this is sometimes called the octet rule, because an atom will lose or gain to try to get to 8. Why 8? Well, because it's that magic full shell for most of the atoms that we're going to look at. This example that we see here is showing sodium and transferring the electron over to chlorine. So if we remember, sodium has an electron configuration of 1s2, 2p6, and 3s1. So what they've done here is they have drawn what's called an electron dot structure. The electron dot structure only shows the valence electron for sodium. Not that we don't care about the rest of the electrons, but the valence electron is the one that is going to be involved in bonding. So since we have one valence electron for sodium, they draw one dot. Chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. So chlorine, on the other hand, has 7 valence electrons, which is why chlorine has 7 dots around it. Now, chlorine is more electronegative than sodium, and so what happens when sodium and chlorine get nearby each other, atoms of sodium and chlorine get nearby each other, sodium wants to send this electron on over to chlorine. And in doing so, by transferring this electron, that arrow is showing the transfer of electron, what will happen is that, I'm going to switch colors here. Let's go to red. What will happen is this 3s electron for sodium is gone. And so what that means is that sodium now has a full shell, a full valence shell. It just happens to be on energy level 2. Because that electron came over to chlorine, now chlorine will have a full shell at 3s2, 3p6. So this is a mutual benefit type of thing. Sodium needs to lose one electron and send that electron over to chlorine. Chlorine needs to gain one, and in doing so, they both get their full valence shells. Now, once that electron transfer happens, we have created an ion. Sodium gets a positive ion because what happens when you lose an electron is now I have more protons than I have electrons. And that's where my positive charge comes from. When chlorine gains an electron, now I have more electrons. And so that's why chlorine always takes a negative charge. So the charges kind of confuse people because they want to think about addition and subtraction, because chlorine is adding an electron. So they want to say, oh, well, chlorine should be positive. But that's not actually what that sign means. That sign isn't addition and subtraction. That sign is looking at the comparison between protons and electrons. If I gain an electron, then I now have more negative charges, which is why it takes a negative charge. If I lose an electron, I have more positive protons. That's why losing an electron makes a positive charge. Now, if we look at that, when sodium loses an electron, it becomes positive, and when chlorine gains an electron, it becomes negative. One of the things that is super important when we look at ionic compounds is that their charges have to cancel. And so in a correctly drawn dot structure or correct ionic bond, we will have an overall charge that is 0. Now, how do I know if an element is going to lose or gain electrons? Well, we said a second ago that it is based on the periodic table and its electron configuration. So if I come up here and look at my periodic table, group 1, they all are going to end in S1, which means they all have 1 valence electron. It will be much easier to lose 1 valence electron like sodium did than it would be to gain 7 more, because I would have to gain 7 in order to get a full octet. Gaining 7 electrons would mean that a lot of energy changes hands, and that's just not something that will happen. And so it's easier for group 1 to lose than it would be to gain. And that's why sometimes you'll see on periodic tables the charges drawn up above it to tell me that this group always is going to make a +1 charge. Similarly, group 2, they all end in S2. So if they all end in S2, they would have to gain 6 in order to get an octet. Well, it's easier to just lose those 2 valence electrons. And so that's why we see the +2 charge written above group 2. We skip over the transition metals because, a little note here, the transition metals, their charges can vary. Sometimes they can be +1, sometimes they can be +2. It really depends on the situation. And we can look at some examples of those as we move forward in this class. But for right now, for this lesson, we just are going to say that the charges vary. For our next group, they all end in S2P1, which means they're going to have 3 valence electrons. Again, it would be easier to lose 3 than it would be to gain 5. Carbon's group, which is this one, it has 4 valence electrons. It's going to end in S2P2, which is where the 4 valence electrons comes from. And this is a midway point. Some of the atoms in this group will lose 4, some will gain 4. And it tends to be that our nonmetals are going to gain and our metals will tend to lose. But this is a little asterisk here. This group doesn't always play by the rules. Our next one is where we actually see elements start gaining instead of losing. So nitrogen's group ends in S2P3. So that's where the 5 valence electrons comes from. And since they already have 5, they need to just gain 3 more. If they gain 3 more, that's where my positive or my -3 comes from. The next column, they are S2P4s. That's where we have our 6 valence electrons from. Since I have 6, they only need to gain 2. Gaining 2 electrons would give a negative charge. And fluorine's group would be S2 and then P5. So 2 and 5 is where my 7 valence electrons come from. Since they have 7, they only need to gain 1. So again, these charges that are kind of at the top of each column, they're based on the electron configurations, how many valence electrons there are, and how many would need to be gained or lost in order to get that octet. Remember, if they only have 1, 2, or 3, it usually is easier to lose those. It's more favorable energy and energy transitions. Once we get to 5, it's more energy favorable to gain instead of lose. Our last group, our noble gases, all of them end in S2P6. And so they already have the full octet, which is why they typically have no charge. All right, so let's look at some examples as we might do some ionic bonds or some ionic compounds. Calcium is in group 2, which is why I've written the symbol calcium with a +2. I know that calcium always ends in S2, and it's going to be losing those 2 valence electrons, forming a positive 2 charge. If you have a periodic table, it might be a good idea until you remember these charges to write them at the top column. So all of hydrogen's column is +1. We've got beryllium's column, which is +2, which is where we have calcium that we just looked at. We'll skip over the transition metals. We've got boron's group that is +3. Carbon's group is the one that can kind of go either way. Nitrogen then will start gaining electrons, so nitrogen group ends up being usually -3, -2 for oxygen, -1, and then our noble gases have no charge. So what they want me to pair with my calcium ion is chlorine ion. Well, chlorine forms a -1 charge. And so the formula for this is going to be CaCl2. Now, how did I know that that was going to be the formula? Well, remember a second ago I said that the charges always have to add up to 0? If I have 1 calcium and only 1 chlorine, my charges do not add to 0. And so if I had a second chlorine, together those would give me a -2 charge, and now they would cancel out to be 0. A +2 cancels out with a -2. And so the way I would write that is calcium, Cl, and then 2. The 2 is to show that I needed 2 chlorines. I don't write a subscript if I only have 1 of something, so I did not write it like this. I wouldn't write the symbol if I didn't have at least 1 of them. That would be like people in math class writing 1x. Do we ever see the 1 written with x? Usually no, because it's implied. My next example, I have calcium with oxygen. In this one, my charges do balance. Calcium's +2 charge, oxygen's -2, so those would cancel each other. I'm already at 0, which means I just need 1 of each. And then my last example is with calcium, and we've done a couple, it's +2. Nitrogen, though, is -3. And whenever you've got kind of weird set of numbers like this, a 2 versus a 3, I always like to think, what is their least common multiple? And the least common multiple between calcium and nitrogen is 6. Or 2 and 3. The least common multiple between 2 and 3 is 6. So if I have a +6, it would cancel with a -6. So a +6 is going to be 3 calciums, and then a -6 would be 2 nitrogens. So again, charge balance, super important, and that's where they got the Ca3N2 from, is because I needed 3 of the calciums to get +6, and I needed 2 of the N's to get -6. All right, so next they want us to complete the following table. And all they're asking for here is a noble gas configuration, how many valence electrons there are, the dot structure, gain or lose, and what charge it would make. Let's start first with strontium. Strontium is number 38. I'm going to put a little box around it. And they are asking for the noble gas configuration. So this is a nice review. The closest noble gas would be krypton without going over. So what I would do is I would put krypton, and we usually put krypton in brackets, and then I'm going to pick up from krypton. So krypton would end 4p6. So what would come next would be 5, and luckily there's a little 5 there. 5s1 would be rubidium, strontium would be 5s2. So this is going to end in 5s2. Which means strontium has 2 valence electrons. The dot structure for strontium is going to have 1, 2 dots. It would have to gain 6, or it could lose 2. It's going to go with the path of least resistance, so it's going to lose 2, which means it's going to have a +2 charge. Sulfur is the next one they want us to look at, which is over here. Sulfur, the closest noble gas is neon. So I put neon in brackets, and I'm going to pick up from neon. So neon was number 10, so I go to 11. This is going to be 3s2. And then remember, we go straight across, and then this would be 3p1 for aluminum, 3p2 for silicon, 3p3 for phosphorus, 3p4 for sulfur. So one of the things that's nice about this noble gas configuration is it shows only the valence electrons, which is super nice. So here in my valence electrons, I would have 2 plus 4, which is 6. The dot structure for sulfur would have 6 valence electrons. And when I'm putting my valence electrons into my dot structure, I always start and go like 6 o'clock, 9 o'clock, midnight, and then you can pair them up. Now, this particular one already has 6, so it's going to be in the gain section, and it's going to gain 2. And remember, if you gain electrons, that means you are adding more negative charge. So it's going to give us a negative charge. All right, next, aluminum is in the same period as we just saw with sulfur. So it's going to look very similar to sulfur, except for the ending. Instead of being P4, it's going to be P1. So we're still going to use neon because that's the closest without going over. It's going to be 3s2, 3p1. How many valence electrons do I have? I have 3. So aluminum's dot structure would be 1, 2, 3. And remember, 4 is kind of threshold on whether you gain or lose. Since we're under 4, we are going to lose those electrons. It's going to lose all 3, which is going to give me a positive 3 charge. Next one to look at is phosphorus. Phosphorus, again, is in the same group. So it's going to be very similar to the other ones we looked at. It'll just differ in the ending. So neon. For sulfur, it was, but for phosphorus, this is just to the left. 1 square. So instead of ending in P4, it's going to end in P3, which gives us 5 valence electrons. So if we go 1, 2, 3, 4, and then you can double them up. This one is going to need to gain. And how many is it going to gain? It's going to gain 3 so that it gets a full octet. When you gain electrons, are negative, so we get a negative charge. Now for neon is one of our noble gases. So remember, the key is to use the closest noble gas without going past neon. So I would actually do helium as my bracket, and then neon is going to go 2s2, 2p6. So it actually has a full shell already. It has 8 valence electrons. It has that octet. If I wanted to draw a dot structure for neon, it would be 8 electrons. Remember, I like to put 1 to each quarter before I start doubling them up. And it's not going to gain or lose any because it already has a full shell, which means it has a charge of 0. All right, a couple more examples here that we'll go over. Number 2, they want to say for each of these symbols, indicate the group on the periodic table for which element X belongs. And so remember, these Lewis symbols or Lewis dot structures, they only show valence electrons. So if we know how many dots are here, we can figure out what group they're in because every group has the same number of valence electrons. So this one having 4, that's kind of a poorly drawn 4, that's going to end up being carbon's group. And for valence electrons, it can gain or lose 4. The next one is the group that would end with 2 valence electrons. And so my group that ends in 2 valence electrons is beryllium's group. So beryllium is always going to lose 2 valence electrons. So 2 valence electrons is going to be beryllium's group, which is known as group 2. And then this last one has 1, 2, and then 3, 4, 5. So 5 valence electrons, that's going to correspond to 1, 2, 3, 4, 5. That's going to be phosphorus's group, which is technically known as group 15. For this next one, they want us to give the name and formula for each of the following combinations of elements. So for here, we just need to know what the charges are, because remember, the key in this game is that charges have to balance. So lithium being a +1 and sodium being a -3, I need a +3 to cancel out a -3. And so that's why lithium, when it combines with nitrogen, you would need 3 of them. The name for this is pretty simple. You simply change the ending of the second element to "ide." And so this is going to be lithium nitride. For sodium and bromine, their charges are +1 and -1. So I actually don't have to do any charge balancing for those because they already cancel each other. And this would be called sodium bromide. For K and S, K is +1 and S is -2. So in order to get this to cancel, I would need 2 potassiums. If I had 2 potassiums, that would give me a +2 to cancel out the -2 of sulfur. And again, this would just be called potassium, and then sulfur becomes sulfide. Barium and fluorine. Barium is +2, fluorine is -1. So that would be BaF2, also known as barium fluoride. Barium and chlorine, their charges cancel, so that would just be CsC, and we would call it cesium chloride. Calcium and phosphorus. Calcium forms a +2 charge, and phosphorus forms a -3. So this is one of those examples where we need to get a least common multiple of 6. So if I need a +6, that would mean 3 of the calciums, and a -6, I would need 2 of the phosphoruses. So that would be Ca3P2, and this is called calcium phosphide. And then the last one of this set, we've got aluminum. Aluminum's a +3 charge, bromine is -1. So I actually need more bromines to cancel this out. It would be AlBr3, and we call it alum bromide. All right, last example before we wrap this up, we have predict some of the properties of element 115. And so 115, if we come down here, is in the same group as nitrogen, phosphorus, arsenic, antimony, bismuth. And it does have a name, moscovium, but it's definitely one of the newer elements on the table. So the first thing it says is, what will its electron configuration be? And I'm going to just focus on the ending part, because the ending part is going to show me my valence electrons. And we can do it as a noble gas configuration. So noble gas, the closest without going over, is going to be 86. So element number 115 is moscovium, and it is in the same column as nitrogen. So I can bet that it's probably going to have at least some similarities to the other elements that are in this group. So on the first part, it asks, what would the electron configuration be? And I'm just going to focus on the last little bit of it. It's going to have a 7s2, and then this would be 7p1, p2, p3. So over here, I know that it will probably end in 7s2 and then 7p3, which means it's going to have 5 valence electrons. And then the next question, it says, what element would it most likely resemble chemically? And based on what we know about groups, I would probably say bismuth. All of the elements in this group are going to have the same valence electron structure. But remember, how high or how low it is depends on things like that attraction to the nucleus, and that can affect lots of the chemistry. So I want to pick an element that's in the same column, but we would not pick nitrogen's too small an atom. It's going to behave a lot differently than probably bismuth would. And so that's why I'm picking one that's further down and closest. So I would choose bismuth if this was me. All right, that wraps it up for 1.8. I hope you got something from this, and that's it for Unit 1. Woohoo!